All right, so in our new packet, but it's filled with old stuff mostly, we're going to be looking at parametric equations today. They're going to kind of feel reminiscent of the old quadratic functions where you would be modeling like how far did the soccer ball go when somebody kicked it. It's those kind of questions. But what we're going to do is, because the horizontal position of the ball and the vertical position of the ball can be related to each other, we're going to be writing them as a series of parametric equations. So the thing that they're going to have in common is time. So at like 1.3 seconds, you should be able to measure for me how far out the ball has traveled and also how far vertically the ball has traveled. And that's what we're going to be doing today. These are some images from your textbook. So I like this one the best to kind of explain what we're doing today. So if we are measuring for a projectile, we're measuring time on the x-axis and vertical distance on the y-axis. This is the typical Algebra 2 question that you guys would be doing. So your teacher would ask you questions like, when does the ball hit the ground? And when does the ball hit the maximum peak? And those would be things that you could measure on your quadratic function in Algebra 2. And we did this in PreCalc even. But remember, it's measuring time versus vertical distance. Well, you could also measure horizontal distance. So like soccer player kicks the ball, the horizontal distance, I mean, unless some weird wind gust comes in, like it's just going to keep going and going and going until eventually the ball is just going to stop, right? So it's kind of weird to measure the horizontal distance against time because that's not usually something we looked at. But what if we put those two functions together? So this is how we create what's called a parametric equation. So you're going to be measuring the horizontal distance along the x-axis, which kind of seems intuitive to me. And then the vertical distance along the y-axis, again, kind of seems intuitive. And the variable that they're going to have in common is the parameter t, because time is something that they will share together. So one of our skills today is going to be rewriting the parametric equations in rectangular form, and then eventually our goal is to be able to go between the two forms. Rectangular form is the form that you guys know and love, just x and y. And then parametric form is the one that we're just introducing you to today. So we're going to go both directions with these formulas. It's going to be a hoot. You're going to love it. You're going to do lots of work on your calculator. And I'm going to warn you, they're a little tedious when it comes to like graphing a parametric equation set because you got to plot a lot of things. So, sorry. T is called the parameter today, okay? T, time, is the parameter. And orientation of your graph, we're going to have little orientation arrows. You're going to have to show me where it begins and ends. And I'm going to show you something cutesy your calculator can do as far as graphing mode. And it's literally going to emulate, like, if it's a problem about someone kicking a soccer ball, it should look like a soccer ball floating through the air. Like, it should make a lot of sense to you when you look at the question. All right, so on our worksheet, we're going to have a function for x and a function for y. They're going to be separate, and because we're going to be in parametric mode on our calculator, we're going to be able to graph these at the same time. So this is one that's, don't worry about this one, but this one's been done from your textbook. They gave them an equation for their x component, and then they also gave them an equation for their y component. So here they are. And I'll show you in a minute how we do this on our calculator. I don't think this is the one that they gave you, right? No. Okay. They graphed it on the time interval of -4 to 4. Now, if this was an application question, time of -4 wouldn't really make a lot of sense, but for some reason they wanted you to graph this from -4 to 4 in your book, so you did. And then what happens is you get a series of ordered pairs. So this is something your calculator is going to spit out at you. Obviously, this is something that we could do by hand, but I wouldn't make you because it's a waste of your time. Now here's the important part. When you are graphing this, this is the starting point. Remember how your time started at -4? So when you go to plot the ordered pair 21, 2, this is like the end point of the parametric equation. And then you keep plotting, but notice the other thing they added to their picture were these little orientation arrows. So you're showing your reader, like, this is how the ball, or whatever it is traveling according to the parametric equation. Clearly this is not a real-life application. Things don't travel like this. I mean, I don't know, maybe they do. A boomerang? I have no idea what this is. So it's just some weird parametric equation. And then remember, it ended at 4 seconds, so it ended back at the same horizontal position, but not the same vertical position. Okay. So that's like the first homework question you have. It's going to look like that. It's going to be a nonsense parametric equation where you just have to type it in your calculator and get some ordered pairs. So let's practice that together. Let's look at this question. So you're going to want to go to your calculator and you're going to put it in parametric mode, which I've already done mine, but they give you an equation for your x and an equation for your y. And then we'll worry about the other part in a minute, but for now, everybody on their calculator, make sure your mode is in parametric instead of function mode. Don't worry about degree and radian right now. It will matter later on in the lesson. We're going to have to put it in degree mode, but for now, it's okay. And then when you go to y equals, since it's no longer in function mode, it's in parametric mode, you're going to see an x and a y component that you need to type in. You'll also notice when you guys use the variable key, it's not using x because it's not a function. It's a parametric function, or a parametric equation set, so it's using t for the parameter. So you don't have to physically change anything to t. It knows that it's t because it's parametric mode. So get those typed in. Do I have them typed in right? Yes, cool. And then we're supposed to fill out this table. Well, you would go to your table for that. Now, because it's counting by integers, if your table is already set up to count by integers, you can just scroll around and find the numbers. But the other thing you guys can remember to do is in table set, you guys can put it in any mode and any counting that you want. So like we're going to have a question coming up where I want it to count by like 1/10 of a second, because it's going to be a real life question about like someone kicking a soccer ball or something like that. So for now, I don't really care. I do want it to count by ones. My table technically starts at -3, so if you want to change it like this, you can. I just have it autofill, and then I just copy the table over. So please copy the table all the way down to 4 for time. So once we have our t, x, and y table filled out, you guys have a series of ordered pairs that you're going to have to plot. And remember, this is the starting point. This is the starting end point. That sounds weird. And this is the end point. So when I ask you for the endpoints, you can fill them out right here, actually. The endpoints are from -1512, and then it ends at 1319. Whoops, that's 19. So now, the fun part, and I use that sarcastically because I think this is torture, you have to plot all of those. And when you connect the curve, you have to draw orientation arrows as well. I'm going to pause the video because I don't think the internet needs to watch me plot. So now that you have your endpoints plotted, remember this was our starting point. You're supposed to connect the curve. Oh boy. Oh gosh. Okay. And then don't continue on because it does end here, right? Starting point, ending point. The other thing you're going to have to give me is the orientation arrows that show you that whatever this object is, it's traveling like this. So this is a notational thing that shows my reader how to read the graph, but also that this is a parametric equation that has orientation. And isn't that beautiful? So that looks like the very first question on your test you're going to take from me next time. It's going to look like that. You're going to use your calculator, parametric mode, grab some points, plot them, connect, make sure your endpoints are in the right spot, and your orientation arrows are looking good. Okay. Issues? Questions? You could do that, right? And Hofbauer was really generous too. You used to have multiple questions like that where you had to plot on your homework, and I think she really cut it down to like 1. There's 1 on your homework where you have to do this, okay? It used to be many. So yay, Hofbauer. All right. This is from your textbook, so just kind of watch what they did. They have parametric equations, and they want you to write it in what's called rectangular form. Rectangular form is our Cartesian coordinate plane form, like the kind that we typically use. So if you just want to think of this as normal, that works for me. Rectangular form would be like something that you would see in Algebra 2. So what they did was, because these two equations had t in common, they did a little substitution trick. And because also rectangular form typically is y equals because it's function notation, they plugged the x formula into the y formula, so that way it was in terms of x. So here's what they do. They take the parameter for x, or the equation for x, they solve it for t, so they would divide both sides by -3, and then they take that for t and they plug that in to the y equals version, that part of the parameter, or the equation. So after they do that, they get 1/9 x to the second power plus 2, and they simplify, and that is a rectangular equation. That's like something we could plot in our traditional Cartesian coordinate plane that we are very used to in Algebra 2. If you guys could envision for me, what would that graph look like? It's a parabola, a little fat parabola, 1/9 in front of it. It's been shifted up 2. So if we graphed it in parametric mode on the calculator, remember you're graphing horizontal versus vertical distance in terms of time. So it's not going to it's a little confusing to kids because they're like, oh, it doesn't look the same way it did in Algebra 2. Different functions, so you have to be careful, okay? If you're graphing it in function notation, in function mode in your calculator, that's fine. So this question is kind of like halfway done for you, so let's kind of investigate what's going on here. They have the x equals equation, so they wanted you to first solve for t, which they've already done for you. They added the 2 over, and then they divided by 4. So they didn't really go to town simplifying this because nothing really simplifies pretty. I mean, you could make it into 2 separate fractions, but that doesn't really help you out at all. So then they took that t equals business, and they plugged it into the y equation. So that's what this looks like. Can you guys help me investigate this further, though? When you square a fraction, one of the things you can do is you can square the numerator and denominator kind of separately. So this would be the same thing as saying x plus 2 squared over, and then if I just go ahead and square the 4 and call it 16, that's the same thing. And then this is a little advanced. I don't know how many kids would be looking at this going, ah, yes, obviously. Do you guys see that there's a 1/16 coefficient right here? I mean, now you do because I wrote it in blue, but this is like 1/16 out in front. So this is all of a sudden looking really like an Algebra 2 question, guys. Do you see that this is a parabola in vertex form? Where's your vertex, by the way? -2, +1. It's got a 1/16 out in front. Now, if you want to really go crazy and you want that general conic form, remember that conic form we just got done using for parabolas? That would be where you would start by, well, you could do a couple of things. Most people, if you're rearranging so that this is isolated, I would start by maybe subtracting the 1 over. And then what's that one more step you would do to isolate this x plus 2 squared thing? Instead of dividing by 1/16, could we just multiply by 16? And of course, both sides, always both sides. Some of you forgot that on your test last week. All right, I think we're done. So, fun, nice connection between what we just got done doing and what we're doing now. Okay? Yes, I can't wait to do more, Mrs. Abruzzo. Let's try another. Oh, that was what they wanted. Is that the one we just did? Oh, no, that's a different one. Never mind. Okay, so on your own now, guys, we have the x equals function. I would like you to solve for t. Kind of crossed it off, but solve for t here. So the first thing you would be doing is you would add the 3 over, and then you're going to divide both sides by 4. So t is this, so that gets thrown in right there. All right, here we go. Y equals this thing we just found, x plus 3 over 4. That whole quantity is being squared, the fraction, and then plus 3. So I'm going to use that same sort of trick I just did where I'm going to square the numerator and denominator kind of separately. I'm going to write it as a 16 instead of a 4 squared. But I'm going to leave that numerator in this factored form. So an alternative way to write this would be y equals, there's like a 1/16 in front here, right? So 1/16 x plus 3 squared plus 3. Or if you really want to get fancy, can you guys help me solve for the quadratic squared component? So you're going to subtract 3 over. And then at the last minute here, to isolate this quantity, you're going to multiply by 16 on both sides. And then you leave it. That's the good news about that weird conic form. You don't actually do any work after that. Okay? So, if we ask you this question on a test, and it says write it in rectangular form. This is technically rectangular form. If for some reason I asked you this question and I wanted you to do some work in the conic version of it, so like for instance if I wanted to know the value of p, this version of it right here, this is the one that you could figure out P really quickly. By the way, what is P? I'm a little concerned. It's 4 in this question because remember 16 is really equal to what in your conic formula? 4 times P. Some of you on the test last week when you went to go plug that back in forgot to multiply it by 4. All right. Oh, that was a hoot. Let's do more of that. So, guess what happens on number 1, guys? More graphing. It's a little boring. Can we look at number 2? Can we get to the good stuff? Let's look at number 2. It's got stars, so that's not good. It's not that bad, I promise. Okay? So, in your calculator, put your new functions in. You should still be in parametric mode. And this time I want to graph from t equals 0 to 9. Okay, so stole some points from some friends, thanks. And they gave me all of the ordered pairs for those different t parameters on those two functions. So when we graphed them, and we had our starting in here at 0, 2, and then the final endpoint at 4.5, 5. Again, this is a problem with no context, so I don't really know what's happening in this question. But that's the shape of the curve that we'd be drawing. And if you forgot to put the orientation arrows showing me where it, like what direction it's heading in, that's very wrong for parametric equations. So make sure you have those orientation arrows on there as well. Clearly I didn't do such a hot job of graphing. Now, when you guys want to look at the actual graph on your calculator, there's a little note down here that says when you're graphing, set your t's up to whatever they want. So like for us, the t would have gone from 0 to 9, but for how they want to count by time, count it by 1/10 of a second. And then you'll see a smoother curve. It won't be so jagged and weird looking. You can try doing different zooms, but remember, like, it's probably best if you control it. So like for instance, when I'm looking at this picture, like even before I started graphing, apparently my teacher was indicating to me that your x's weren't going to go too far out, neither were your y's. So you could have easily set up your x and y parameters just based on what you saw in the results, guys. Like x's didn't go any smaller than 0, and they didn't go any larger than 4.5. So I would probably just set up my x's accordingly and my y's as well. Okay? So that is the first challenge for you. On worksheet 13B, there's just a little more of this. So let's do one of those and let's move on to the good stuff at the end here. All right. So they want you to write it in rectangular form, which basically means I needed to say y equals and then a bunch of mess after it. So we're going to solve for t in the x equation. So that's going to look like what? Let's see. We're going to subtract the 3 over, and then you're going to divide everything by a 2. Is this on the back of 13, right? Okay. So this is what you're going to substitute in for t, but into the other parameter, or sorry, the other equation. So y equals, there's absolutely nothing wrong with you guys saying x minus 3 over 2 minus 4. Now notice we don't have that weird like squaring stuff going on in this question because there's absolutely no real life connection to this one right now. There's no component that's being squared, so I'm okay with you leaving that as your answer. You could do some work where like you divide each of these by a 2 and then you combine these constants together. But if this was like a homework question and they said get it in rectangular form, if you're like me, you're going to do the least amount of work possible, so you'd be done and you'd stop right here. Now if your teacher said get it in rectangular form and then graph it, then you might want to do a little more work because this is not necessarily anything that I would like to graph in this form, so I might work a little harder. Alright, I'm going to move on because it's getting kind of boring. Projectile motion, this is the good stuff. So these are the questions where typically for us it's very sports oriented. And what a season for us guys. Soccer, baseball season, perfect. Track, you guys throw stuff sometimes, right? I don't know. What do you people throw in track these days? Discus and shot put? Yeah, that's good. We could write some good shot put questions. But I'll be honest, most of them are soccer ball questions. So the idea is someone's going to project an object by kicking, throwing, launching it. And it's going to cover horizontal distance at the same time it's going to cover vertical distance. And if you think about like any of those ideas, the shot put, the soccer ball, you know, it goes up and then it comes down. But it doesn't stop gaining horizontal distance as it comes down, right? It continues to travel. Yeah. So we're going to write them as parameters. So you have two new versions of the x and y equations, and because it's real life, you have to incorporate your angle, right? People who actually play sports, not me. The angle at which you kick, throw something makes a very big difference. Baseball! Does it matter at the angle at which you hit the ball? Very much so, yes. In fact, there's lots of very smart people who work for professional athletes who coach them through this, and there's a lot of technology involved in it. But the perfect angle at which you hit it at certain speeds, certain types of materials, like it all affects it. So this formula right here is what we're going to use for these real-life questions to measure horizontal distance. It's t, which is time, times the initial velocity at which you hit the object, or whatever you're doing, and then times the cosine of the angle, which is very important to this. Now for the vertical position, the vertical distance, also incorporates some real-life stuff here. So that t shows up again, time, times your initial velocity, times the sine of the angle. And then they do this weird, like they rearrange the formula. If you don't mind, I'm going to throw the -1/2 gt thing in front. Can we talk for a moment about what g stands for? Gravity, the acceleration due to gravity. Now, for most of our questions, because we're so very American in PreCalc, we're going to call gravity's acceleration -16 feet per second squared, because most of our formulas, most of our problems are measured in feet and seconds. But my physics people, what if it's measured in meters per second squared? That was a quick answer, -9.8 meters per second squared, yes. So you might want to make a little note here. If it's meters per second squared, then g equals, whoops, -9.8 meters per second squared. And if it's feet, that's where it's -16 feet per second squared. So this part right here, this -1/2 gt thing, that's going to change. So I'm not going to fill in anything for that right now, but this is just depending on what your gravity is measured in. And then h sub naught, do you remember what anything sub naught meant? Initial, starting, yeah. So h sub naught would represent your starting height, yeah. The formula that we put on your note card, which I do have a note card to give you, I just don't want to give it to you yet because I felt like you picked up a lot of stuff today. I'll give it to you tomorrow. It has this red formula in like a more appropriate order, something that you saw a lot in Algebra 2, where the gravity thing is first. So I think it says -16 t squared plus the rest of it in that order. And there's a little note underneath it that says if you're not measuring in feet, that you need to measure in meters per second squared. I will not try to trick you on a test though, guys. If everything we've practiced is in feet, I'm not going to all of a sudden put a meters per second. The only people who get in trouble are my physics people, because you guys are probably very used to using meters per second squared is my guess, right? You guys use meters? Yeah. Your book is American. America. Alright, so this will be on your reference sheet. I think this is the version you'll see, so they use the feet, and then there's a little note that, oh yeah, kind of forgot about that. Remember how it's 1/2? Yeah, it's not -9.8, -4.9, because the half is in there. They incorporated the half already. You guys don't need to worry about it. Here's the thing. On homework, I'll double check for you, but I don't think any of them are measured in meters. We'll get to that. All right. Oh, basketball. How could I forget basketball? Because it's not basketball season, Abruzzo. All right, so Kaylee is practicing free throws for an upcoming basketball game, and she's going to calculate it. This is my kind of girl. All right, so the initial velocity, that's an important key feature right there, guys. The initial velocity is 24 feet per second. So that clue right there, and I don't think this is on your paper anywhere, is it? We got Luigi coming up. We'll talk about Luigi in a minute. That's her initial velocity. The angle is 53 degrees. That's her release angle with the rim. It's measured at the rim. It's got to be measured with something horizontal. So depending on where they're perceiving this to be. Notice they measured in degrees. So when you're typing this in your calculator, if you're going to enter it as 53 degrees, what else do you have to be worried about in your calculator? That your mode is in degree mode. Okay, so we're going to be in degree mode for these. Blah, 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 horizontal distance. I can't read because I crossed off half of it. Okay, so 13 feet. The vertical distance of the floor is 10 feet. The front of the rim is 2 feet from the backboard. So they're just trying to help you set up your window and all those clues, because obviously she's not going to be launching the ball halfway across the court unless she's really bad. So your window should be appropriate for what she's looking at in the basketball court. And then it does say she releases it at 4.7 feet from the ground. So that's that initial height. So when you're kind of reading through these questions, you got to go pick out all the information. Okay? You don't have to do this, guys, but we would be in parametric mode. We would use that x formula, and they wrote down 24 times t times the cosine of 53, and then for the y formula, because it's feet, right, they did negative 16 t squared plus 24t sine, you can't read the rest of it, but it's sine of 53 plus the initial height, and then they graphed it. Now on Luigi's question, I'm going to show you something kind of cutesy your calculator can do. You don't have to use it, I just think it's kind of fun. Let's talk about Luigi. He's kicking a soccer ball. And he kicks the ball with an initial velocity of 35 feet per second. So there's that initial velocity. The angle with the horizontal, always measured with the horizontal, is 48. So there's that theta. And the ball is 2 feet above the ground when he kicks it, because he does one of those cool kicks, like he kicks in the air, kind of. So that's his initial starting height for the ball. So they want me to make a diagram, and I'm not going to, but I'm going to totally write functions out. So using our formula for x, you can do this multiplication in any order you guys want, but I tend to forget to write things if I don't write it in this exact order. So what I'm going to write down is t times the initial velocity times the cosine of 48. I know that's not the exact same order that the formula sheet will say it in, but if I don't put the t first, I forget the t, like every time. So then for the vertical position, because it was measured in feet on this one, right? Yeah. So we're going to start with, I always start with gravity, so I go negative 16, and then t squared. Notice I'm using these weird capital T's. That's because that's the variable, that's what it's going to look like in parametric mode, okay? Plus t times the initial velocity again, but then it's times the sine of the angle, and then I'm drawing on Luigi's face, plus the initial height of 2. So obviously the vertical component formula has a little more going on to it. But that looks very much like an Algebra 2 equation, except for the weird insertion of the sine and the cosine, doesn't it? That's weird. All right, so get these typed in parametric mode. Okay, I don't play soccer, and I never have, but they don't really tell you anything about parameters for the time. So someone who has either watched or played soccer, give me a good appropriate window for time for how long the soccer ball will be in the air. Like, I know to start at 0, but where should we end? How long would the soccer ball be in the air? I don't know. Jaden, this is your moment. Like 5 seconds? Longer? Sure. I mean, like 10 seconds would be too long. That's like crazy, right? Okay, let's go 5. Now notice it says, go ahead and count by point ones when you graph it. X is measuring horizontal distance. Again, I don't play soccer, never have. Horizontal distance for how long a soccer ball would travel. No clue, but I know it starts at 0. It's 50 feet too far? I know, we're preaching to the choir here, aren't we? I don't know. I'm going to try 50, I'm just guessing. And then vertical distance, how high up in the air would it go? Is 30 too far? I don't know either. Come on, soccer players, step up. I need your help. All right, I'm going to pause the video while I get all that entered. So I'm sure I typed something wrong at this point. Make sure in your mode that you are in degree mode, because remember we're measuring that angle in degree. And then I haven't adjusted any window yet, but my friends have, and they told me I should scale back something. I forgot what we said for time. Did we say 10? 0 to 5, that makes more sense. 10 is crazy. And then we need to make sure it's stepping by tenths of a second. And then you guys told me the x was 0.50 was good? Okay. So he had the distance, but the verticalness was just too much, huh? 0 to 20, okay. I originally thought 30, but that was too crazy, huh? Okay. Now, if you hit graph, it's just going to, boom. I think that's beautiful. Now, can I show you something kind of cutesy? You don't have to ever do this again. I just want you to know it's here. If you go back here to where you have color options, can you go select that? Let's explore that menu for a moment. Colors are great. I love changing colors, but if you go to the lines, there's a lot of options here. This one right here, if you scroll to the right, what it would do is it would draw the parametric curve, and it would also draw like a little ball. It'd be like watching a soccer ball go by, okay? And if you go one more time, this time it's not going to draw the curve with it. It'll just literally draw the ball. I don't know why you'd want that, other than animation. I guess when you're writing, like, you know, those games they have, and there's like there's one where like the basketball bounces. Yeah, like that's probably why they have that option. Otherwise, I don't know why you'd want that. So I'm going to go back. I'm going to draw this one for funsies. And just watch carefully because it goes kind of fast. Wow. Wasn't that cute? That was like a big deal back in the 90s, guys, because they added that feature and we were like, whoa, you can see the ball. Yeah, all right, you're not impressed? Fine. Whatever. Go do your homework. Now, we have more questions to answer, don't we? There's some questions about Luigi, and it says, find the time that the ball hits the ground. So there's a couple of places you could do this. Unfortunately, your calc menu doesn't really work well in parametric mode. So for most people, they either trace it or they go to their table. And remember, they're looking for when it hit the ground, so that means the vertical height. So you're watching for the, oh, what's going on here? I didn't fix my table. Do you guys remember how we were supposed to count by not integers? I would go to table setup, and I would change my table to count by something small, like 0.1. That would be great. And I'm not going to start at -3. That would just be goofy. Let's start at 0. Now when I go to my table, I'm going to watch the vertical position and see when it hits the ground, and I can see it a little more closely. And this is a great way to do the... Okay, I should have probably scrolled out a little bit more. Yeah, this is going to take forever, guys. Go back to your graph. Can you hit trace? Start scrolling along the way. Oh, too far. Come back. Okay, so do you see it? What does all this information mean? So t is 1.6, it's up here. T is 1.7, it's down there. So it must hit the ground in between 1.6 and 1.7 seconds. Am I the only one who got that answer? No, you have it too? Cool, cool. Okay. Now, when you go to your table, since I know the answer is secretly between 1.6 and 1.7, oh yeah, I guess I was there. I got a little impatient. You guys see it's going to hit the ground right here? It goes from positive to negative height, therefore it went to the ground. Okay. It's also going to ask you how far did the ball travel when it hits the ground. So like if there's a player he's trying to get to, well, it hits the ground right around here. So the ball traveled how far? What's the horizontal distance? About, let's say 38-ish feet. Yeah. So hopefully he did his mental calculations properly and he got his leg to work and then he got the ball to the right dude. Good job, Luigi. And then it says, how high did the ball get? Well, there's a couple of ways you could figure this out. You could watch the vertical distance and see when it turns around, essentially. So like if you back up in the table. I notice it goes like as high as 12.6-ish, and then it turns back around. So right in that area is where it reaches its maximum. The other way you could get that answer is to look at your graph and using your trace feature to scroll towards that maximum. You cannot use the maximum finder in parametric mode, so that's out. So you have to use one of these other options, okay? And the other question was, if a 6-foot defender is standing 35 feet away, will it clear him? Well, remember we're measuring in feet, so we don't have that problem. 35 feet away, watch your X's. Here's 35 feet, huh? 35 feet out. The ball is 5 feet up in the air. So is it going to go over that dude's head? No. It's going to smack him right in the neck or something. I don't know. That dude's going to stop that ball. All right, so those are the kind of questions that we could answer. So those are the kind of questions you're going to be asked on your homework and also on your test coming up. Don't ask me when the test is, guys. We got a 3-day week. We just got to make it through, okay?